So good morning to those in India and hello to the rest of the world. A very warm welcome to this first keynote lecture of CODS COMAT 2021, which will be delivered by Professor Divyakant Agrawal. Divi, as he is more affectionately known, is a legend in the database research community. He received his bachelor's degree from BITS Pilani in 1980, graduating at the very top of his class. Then, after a brief stint in the then nascent Indian software industry, he moved to the United States for his graduate studies and completed his PhD from Stony Brook in 1987. Immediately afterwards, he took up a faculty position at Santa Barbara and has continued to be with them for the past 3 decades. During this long tenure, he has also served as the department chair. Divi's exceptional contributions to distributed systems in general and databases in particular, which amount to more than 400 papers at last count, have received numerous recognitions. He is a fellow of ACM, of IEEE, and of AAAS, and has also been the long-time editor-in-chief of the Journal of Distributed and Parallel Databases. On a personal note, I first met Divi in the early 90s when I was about to graduate from Wisconsin, and he has subsequently been an exceptional mentor to not just me, but the entire database community in India. So it is a privilege to request him to kindly deliver the inaugural keynote lecture, where he will educate us about the role of blockchain technologies in big data deployments. So again, before we start, a request to the audience, please post your questions on the Q&A channel, and we will convey them to Professor Agrawal at the end of the lecture. So with that brief introduction, over to you, Divi.
Divi, you're muted.
Yeah, Divi, you're still on mute.
Thanks, Jayant, for those kind words. I'm indeed very honored to be here, and I want to thank you and Sharath for choosing me to do this talk in these trying times. But this is the start of a new year. I want to wish you all and all of us a happy new year and a better new year, hopefully. And with that, I'm going to speak to you about the topic I've chosen, demystifying blockchains for big data. So the notion of blockchains has emerged as one of the most promising technologies recently. Now, although the blockchain emerged as an underlying storage platform, primarily in the context of cryptocurrencies, for the past few years, they are being projected as the ultimate storage infrastructure for future applications. So the goal of my presentation is to basically spend the next hour or so to understand what this underlying technology is and perhaps ponder on the question if indeed this is the future of decentralized and fault-tolerant storage for big data. I just would like to mention is that I'm not, this talk should be viewed more as an advanced technology presentation. I do have some of my research results, but it's primarily integrating information from lots of sources. And what I would like to do is, before I begin my presentation, I would like to acknowledge my collaborator for almost 30 years, Professor Amr El-Abadi. As many of you may know, that I have worked very closely with him, as well as our graduate and undergraduate students, some of whom are no longer students anymore. So there is Ishtiaq, Muhammad, Sean, Sujaya, Daniel, Victor, and Fuhang. So as academics, we really have to acknowledge the work that is done by our students, and I'm really indeed grateful for these students as well as many others who have worked with me in the past. So let me, so the question is, why should we, from a database point of view, be interested in this particular technology that is really primarily in the context of cryptocurrency and has made a big impact there. And the reason we need to really look at this technology is it does have some very interesting properties that, from a database point of view, we have all kind of researched and looked at it in different contexts. And it brings together all those elements in a single storage platform. So one of the things is it has this notion of transparency, where unlike in the in most database system, the data gets logged in and only privileged users have access to it, or very kind of restricted access to it. Here, the data, the blockchain itself is available to any party and it can be accessed for variety of purposes. So it has this notion of transparency. It it also has this notion of provenance, which I think in the database context, there has been a lot of research in the context of data provenance, and it provides you this property from first principles. There is fault tolerance associated with it because it is, this blockchains are highly replicated by replicating the ledger over all the network nodes, and that gives you a significantly high degree of fault tolerance. There is the database property of immutability, that is, once the data is added, it cannot be altered or tampered. And finally, there is this, because of a lot of the cryptographic protocols that I use, there is some level of trust and authenticity associated with this data. So these are some of the properties, and the question is, how does it do that, and how does it come about? So that's kind of is what I'm going to be unraveling as I go through the next few slides. So the best way to understand the blockchain platform is to understand it in the context of the cryptocurrency application. That's what they were designed for, and I think it is very easy. It's much easier to understand how this particular technology is used in the context of cryptocurrency. So what you have to do is you have to look at the notion of the banking in the classical sense, where basically we have these banking institutions which are trusted entity who manage our accounts, and we as clients interact with our banks. And when we have to interact with each other, and if we are associated with different banking institutions, what we have to do is we have to facilitate our interaction through our trusted partners, which are these banks. Okay, so the facilitation of people who are interacting across different institutions have to be managed through these intermediaries. So kind of looking at it, what are the necessary ingredients in the traditional banking systems? If you look at it, basically, you are identified as an individual or as a customer of a bank through your identities and signatures. So you are your signature, ID, user, and name and password. For example, your ID is used in a physical context, username and password are used in a digital context, but that's how you are known to the bank. The bank in turn basically maintains the information about you in the form of a ledger, which is saved in a classical database. Okay, and the interactions that you perform are managed through transactions, which allows you to move money from one identity to another. There is a you have to make basically you have to make sure that you don't overspend, or if you initiate multiple transfers, things are controlled by the bank through the classical techniques like concurrency control and serialization. And typically there is a log that is maintained, which is make sure that you have all the information is available. So the log itself is persistent, it is immutable and tamper-free because we trust this central institution. Okay, so in 2008, there was a kind of a paper by an anonymous author who goes by the name Nakamoto. And the interesting thing is this paper is not published in any of the established academic or research venues. It appeared as just an archival paper. And what this paper proposes is that why should we have a central entity to maintain the notion of currencies and accounts? Okay, so this paper, which is barely 6 or 7 pages, and essentially what it proposes is to use the network as a replacement for the centralized notion of a banking institution or a database. Okay, and it combines technologies from cryptography, from databases, from distributed systems, distributed computing. It brings all these things together to propose a very intriguing approach of managing data in a completely decentralized system. So this is I think in some sense it is a revolutionary paper, and what we have seen in the last decade or so is that it has had a significant impact. For example, I just would like to mention is that the market capitalization of a Bitcoin exceeds the market capitalization of some very well established companies which have been around for hundreds of years. So this has been really a remarkable result that has had a major disruption in the technology arena. And I think that is the reason we need to make sure that we understand what this technology is. And the question is whether this technology as is can be used in many of our applications that we are intimately familiar with, or is there something that can be learned from there? Okay, so that's kind of is my goal in the next few minutes to be able to. So so just to contrast in the context of the Bitcoin and blockchain, what happens is the identities and signatures are replaced by the well-known idea of public-private keys that have been around in the cryptography arena for a long time. The ledger is replaced by the balance for each identity, which is somehow managed and saved in the blockchain. And the transactions are moving these cryptocurrency from one identity to another, which is again managed as transactions in these data blocks, which are maintained in the blockchain. There is a question of in the context of these digital instruments, what you have to worry about is that people could make multiple copies of that digital instrument and try to leverage that to overspend more than what they have, and that is controlled by a very powerful notion of what is referred to as mining and proof of work. And finally, the transaction log is basically represented as the blockchain. And this log is persistent because it is replicated across the network nodes, and it is made immutable and tamper-free by a combination of cryptographic techniques and this notion of proof of work that I'm going to explain in a little bit. But these two techniques allow it to become almost tamper-free. Okay, so one thing I want to mention is many of these guarantees that are made these are probabilistic guarantees, which is very different than what we provide in the database context. For example, the guarantees that we provide are more deterministic in some sense. Okay, so I have to be careful about time anyway. So the basic ingredient, one of the first ingredient is that the transactions or the instrument that is used is these signed documents, which is a combination of public key and private key. So what you do is you basically allow the an initiator of a transaction to 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 sign the document using their private key, and that becomes a signed document, which can then be taken by some other parties, and using the public key, they can verify if the signed instrument is valid or invalid. So this is the properties that are provided is this using these signatures, it can be shown that it is very hard to kind of forge a document, and it is very easy to verify. And in the context of cryptocurrency, the way it works is that basically when I have so if I'm Alice and I want to transfer some money to, let's say, another user, Bob, basically what I do is I take my money and I combine it with my signature and create a signed instrument which says that there is a transfer of money that has to take place from Alice to Bob. And that can be basically put into the blockchain. And by using Alice's signature, it can be verified if it is valid or not. Okay. And and with and this can be carried out, if Bob now takes whatever money has come in, and part of that money, if he wants to transfer to another user, say Diana, then he can just take the instrument combined with the Diana's public identity and create a signed instrument which makes a transfer from Bob to Diana. Okay. And in general, what you can have is you can have a sequence of these transfers that basically allow you to do that. So what's happening here is you have a complete history of how the money is flowing from one user to the other, which is very different than what we see in the context of a physical cash, where the money, you don't really can track as to how the money has moved from one place to the other. Okay, so there are some, issues that arise is that, as the provenance increases, these instruments can become unbounded in size. So how do you make sure you control the size of these instruments? There is also a concern that arises is that you might have a situation where, because it is an electronic instrument, you can make multiple copies of it and you can start distributing to many people at the same time. So how do you prevent double spending? The double spending problem is really can be thought of as a concurrency control problem from a database literature. And finally, the question arises is, how does the money come into being? So 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 these are some of the questions that arise, and I'm going to just say that the combination function is based on this the idea of hashing, where you basically can have a large document to be compressed and be represented in 256 bits. The double spending is controlled by using what is known as a proof of work, and the 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 money comes into circulation as a result of what is referred to as mining. Okay, so so I'm so the just to reiterate about double spending is a significant problem, because what you are doing is you are replacing a trusted entity, a bank, by an open network, right? So what you have to worry about is there could be malicious kind of activity that can go around, and even if most of the people are trustworthy, there could still be some people who are trying to to uh, to cause harm to the system. So the double spending can happen is when Bob can decide to perform a transfer of the same money to multiple parties, right? And the question is, how can the system prevent that from happening? And that's, I think, is one of the critical goal of this endeavor. Okay, so what we just have to understand is we have there are these three critical pieces that we have to understand. What is the ledger? So when we are basically, how do you organize the transactions in the ledger? And the third question is, what are the incentive mechanisms that are provided in the system to make sure that all the network nodes kind of maintain the ledger in the same way, right? So since you are replicating this ledger in many nodes, how do you make sure that they are mutually consistent with each other? What is the underlying incentive that is going to be provided by the system to make sure that things don't go uh, completely haywire? So so let me just so the ledger is essentially a, a linked collection of transactions organized in a block. Okay, so that's what it is. So the one main difference is that in order to make sure that these links are maintained in a consistent manner, there is a notion. What you do is, instead of having ordinary pointers, you maintain a hash of the pointer, and that is referred to as a hash pointers. Okay, so the hash is essentially is some information that has been hashed and maintained in the next pointer, next block, and so on. Okay, so what this means is, and I should get my laser pointer. What it means is that if somebody has modifies a particular block, let's say this block is being modified, then the corresponding hash value has to be updated here. And then since this has been modified, then this hash value has to be updated here, and so on. So if you modify any of the block, if some malicious entity modifies the block in the middle, what happens is all the subsequent hashes have to be corrected in order to make sure that the blockchain is consistent. Okay, and I am going to so that's basically, it's not enough to just modify one hash and be done with it. The effort that would be needed is, if you are interested in tampering in one of the blocks, then it is your obligation to make sure that all the subsequent hashes have been fixed. So in order to achieve a consistent blockchain, and this makes tampering with the blockchain very difficult. And that I will explain as to why coming up with this hash is a significant undertaking. Okay, so so one of the things that we have to do, as you saw in the previous slide, is that in order to make this tampering hard, you have to make sure that updating these hash pointer must be very hard. Okay, and that's is related to it, to the next question that we are going to come up with is that how do you add new information to the blockchain? Okay, so the new information to the blockchain is added, is considered making progress. So to start with, all the network nodes have a copy of this, let's say, existing blockchain. Okay, as new transactions are initiated, the network nodes are going to validate these new transactions, and they all kind of, they have to put these new transaction into into the next block that has to be added. And as part of that validation, you have to make sure that the transaction in the block do not conflict with each other, and they also have to make sure that the transactions do not conflict with the previous transactions. Okay, then the bigger question that appears is, since there are many kind of, that it is completely decentralized system, that what you have to do is somehow these network nodes have to come to an agreement what should be the next block. So if there are two nodes who have prepared a block, the question arises, who gets to go next? And that has to be agreed upon. And in the classical kind of distributed computing context, this could be referred to as a consensus problem. So the distributed consensus protocol in the distributed computing arena, right? We have worked on, variants of these protocols in the context of a network which is only prone to crash failures. There is a very well known protocol which is widely used actually in the current context, which is referred to as a Copaxos. And in the context of malicious failure or Byzantine failures, the protocol is known as a BFT, or Byzantine fault tolerance. The limitation of these protocols is that in both of these classes of protocols, what you have to know is you have to know the kind of the number of nodes that are participating in the consensus. Okay. And in the Bitcoin context, or in the blockchain context, we are dealing with open networks, in the sense that network nodes can come in and join. The notion of n, the fixed number of network nodes, is not known. Okay, so that's kind of makes these protocols moot in the context of Bitcoin. And what Nakamoto proposed is this notion of proof of work, which again comes from the cryptographic. This has been a known result in the cryptography, and it basically replaces communication by computation. Okay, and I'm going to make this. I'm going to make this just at a high level. The idea is basically what happens is that you, instead of making it a collective kind of problem of reaching consensus, where you send messages to each other and try to kind of coordinate the result among yourselves, this becomes more an individual effort. So everyone performs some computation, and and once you become successful in performing that computation, then you kind of share it with everyone, saying that I have done it, and I should be the one who should go next. And this computation that has been done, that has to be done, is essentially solving a cryptographic hash puzzle. Okay, so that's what is the criteria for every new block that has to be added. You have to solve a given puzzle, and once you have an evidence that you have solved that particular puzzle, then people agree on the people give you, defer to you, your leadership, and you the net as a network node get to go next to add a block to the blockchain. Okay, I have several slides, but I'm going to. So this is the high level idea. I am going to skip over this, but the next few slides essentially describe these details. And given the speed at which I'm going, I'm going to skip that. And so so as I said, basically the puzzle is that for the block that you are constructing, you as a network node are proposing, you have to solve a cryptographic hash computation, and provide that as an evidence that you have solved that, and that you share it with everyone. And and, and so whoever is the whichever node gets to solve this puzzle is going to go next. Okay, so once your leadership is established, a block is mine, and block is mine means that you have the right to add the block to the blockchain. Okay, so the underlying theme is that the solving of the puzzle is difficult, but once it is solved and you provide the evidence, it can be easily verified by network nodes. That is not computationally difficult. Okay, some of the criteria, that is some of the things that have to be uh, watched for, is that you cannot pre-compute the information. You can only start working on the puzzle solving once you have the block. You cannot do pre-computation and you try to kind of uh, have an unfair advantage over others. The other thing is, if you are the one who have solved the puzzle, then it cannot be stolen, because the 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 solution gives you the reward. So the reason you solve the puzzle is because you are going to get some um, reward function out of it. That is, there is going to be some bitcoins that are going to be mined from it, and because it is associated with the public key of the mining node, it cannot be taken. Somebody cannot hijack it. Okay, and the network nodes accept the first found block. The problem is difficult. There is no guaranteed bound to find another block. So you can't, people cannot block you by saying, oh, since I'm close to finishing that, I'm not going to accept it. But as soon as it is found, there is an incentive for them to accept it, because if they don't accept it, they cannot start working on their own kind of puzzle for the next block. Okay. um, the problem that happens is that you could have a situation where one of the things that can happen in the blockchain context is two nodes simultaneously and concurrently mine a particular block, at different blocks. In that case, what happens in this blockchain context is this notion of forking, and and the solution is that you basically allow the forks to happen, but eventually what's going to happen is that all the mining nodes are going to kind of rally behind the fork that has got the longest chain associated with it. So the ones which is the chain which is kind of has this failed transactions, they have to be basically aborted and retried later. So in that sense, the guarantees that are associated with blockchain is that they are probabilistic. The commitment of a transaction is not guaranteed until a certain time. I see some chat window. Okay.
Divi, there was one question which by Arjun Ramesh, which said, "What
Yeah.
happens when multiple broadcasts are made by different miners? How do you handle the concurrency in such scenarios?"
Yeah. So Arjun, I think the answer to that question is in the context of folks. Basically, what can happen is you could have a divergent blockchain that is happening, but eventually, what's going to happen is things are going to be stabilized behind the one with the longest chain. So we can discuss that bit later, but that's the general idea. So the guarantees are probabilistic in that sense for commitment of transactions. Okay, so with this introduction, I want to kind of talk about the limitations of Bitcoin. Why we can't. These are all great things, but there are certain issues associated with it, especially from a database context. From our point of view, there is a very high latency associated with transactions. Uh, Typically, so the current estimates are it takes in the order of minutes for transactions to be committed. The guarantees are probabilistic, as I already mentioned, and the throughput in these type of systems is somewhere in the order of 3 to 7 transactions per second, which is really not acceptable. I mean, if you're talking about big data, this is not what we can afford to do. Okay, and a new block is added every 10 minutes. That is what is the estimates right now. Okay, so there are ways you can go about, think about scaling Bitcoin. One of the possibility could be is to increase the size of the blocks. So you can, instead of taking a current size, you can make it 10 times bigger or 100 times bigger. The other possibility is, instead of decreasing the block interval, so meaning what you do is you basically reduce the complexity of the puzzle that you are asking people to solve. And the problem with these techniques is that if you increase the block size, what it does is it favors miners who have more computational capacity and will be able to do, will be able to win the mining competition more frequently than others. And if you decrease the interval, meaning decrease the complexity of the puzzle, what it leads to is it leads to lot of forks, which is also, brings instability in the system. So these are some of the issues. Now, in the academic arena, people have looked at the issue of scaling bitcoins or blockchains. So one idea that came about a few years ago was what you can do is you can separate the notion of adding transactions, new transactions, and the issue of kind of having the right to add new transactions. So you could think of it as you can separate the two things, and what you can do is you can run a mining competition every few, let's say, minutes, and then once you have won the mining competition, you become the leader for the next, let's say, half an hour, and then you have the right to add all the transactions. So you can do that. So you, as you can see, once you have that, then you can do significantly improve the throughput. The problem with this approach is even if you give leadership to someone, so within that half an hour, you cannot trust if they are going to not do any malicious activity. So that's, I think, is the danger that you run into. There is another proposal which kind of is a variant of this, is that in order to eliminate the notion of giving somebody an exclusive access to become the leader, what you can do is you can keep track of the leaders for the last, let's say, 10 epochs. And now what happens is this becomes a collective committee, and what you do is the addition of new data blocks or new transaction blocks is done in the form of a PBFT, a Byzantine fault tolerant consensus among a small set of nodes that you have right now. The other approach that people have looked at is that what you can do is, this is some work from National University of Singapore, where we basically, what you do is, instead of looking at the network as a whole, you basically partition the network into different parts. And I'm going to visualize that in a moment. And the idea with that is that here is a network, and what you do is, instead of looking at the blockchain as kind of an entity that corresponds to the entire network, you can basically partition into a different kind of shard of that blockchain belonging to different networks. So you have a gold network, a blue network, a red network, and the green network. And so you basically have partitioned that, and now you can transact 4 times as many transactions as before in this particular example. Okay, so what are the challenges of that? Well, as long as you are dealing with transactions that are within your network, so essentially you're moving currencies from one user to the other, and they are in the same network, then you can easily execute them locally. So they are single sharded. But the problem arises that when you have kind of access of, you need to transfer information or bitcoins from blue network to the red network, then you have to run what is referred to as a cross-shard transaction. And given that these are completely decentralized system, the problem is that how do you do a cross-shard transaction which is atomic across these two networks? So I'm going to present next few slides and introduce this idea. So this is a very compelling approach of scaling bitcoins, but it does introduce an additional problem of solving the problem of atomicity of cross-shard transactions. Okay, so so let me kind of make this a little bit more clearer, and I think I'm going to conceptualize, and so let's see. So basically, you can think of this as a a cross-shard transaction where you have two users. Let's say Alice has X Bitcoins and you have Bob with Y Ethereum. And what they want to do is, so these are two completely kind of autonomous kind of blockchains. And what they want to do is they have agreed upon through outside the system that they want to perform an exchange where Alice wants to change her X Bitcoins to Bob's Y Ethers, right? So what we need in this case is we need to do what is referred to as atomic swap of these currencies. So you want to make sure that you want to transfer money. So Alice transfers X Bitcoins from herself to Bob, but she also has to be sure that when she does that, Bob has done the same thing and transferred Y Ethers from himself to her. Okay, so that's, I hope you see the complexity that arises because these are completely decentralized system. And the question is, how do you do this atomic commitment where simultaneously the block representing X's, Bob's Bitcoins, transferred Bitcoins, and Alice's transferred Ethers appear on the respective chain. Okay, so you have to do this swap of ownership. Okay, so this idea kind of came about as a blog entry by a person, Nolan, in 2013. So this was not a published paper, but he outlined a protocol to achieve this kind of functionality. I see a couple of questions.
Yeah, Divi, one question was about, you talked about these different colored shards corresponding to networks. The question was, how do you know which network a particular
Yeah,
transaction belongs to?
so that's a good question, Arjun. So here is how you can see it. Uh, so think of your public key and my public key, right? And let's say your public key ends with 0 and my public key ends with 1. So what we can do is we could think of it, you will be in the red network and I could be in the blue network. So that is one criteria, right? So now, and Jayant is also, his public key ends with a 0 bit, right? So you and Jayant can be in the red network and you can interact with each other, transfer currencies, perform transactions. And when you have to interact with me, now we are cross shard, and we have to do that. Does that answer a question? You can
And
see how
Divi,
the
the other
transactions
question,
localized and transactions are not localized.
Divi, the other question is a lot more philosophical. It asks, do probabilistic guarantees work for databases? And you can choose whether you want to answer it at the end of the talk or right now.
Yeah, so let's take that at the end of the talk.
Okay,
I
sure.
um I have my own have my own thinking because we as database professionals and researchers and developers, we claim that we provide deterministic guarantee. But if you think about it, the substrate on which we run is itself probabilistic, right? You can have bit errors at your storage layer. You have bit errors in your memory systems. So I know that we try to overcome that, but the best we do is we reduce the probabilities to very small. Okay, nevertheless, there is always that possibility that something can go wrong, right? Now, so for example, the memory errors, right? The data corruption of bit flips that happen due to cosmic rays and things like that is claimed to be 10 raised to the power minus 16, right? So most applications don't see it, but applications that process hundreds of terabytes or thousands of terabytes of data, some of the companies in the Bay Area do that. They see these type of errors on a regular basis. So that's kind of is my position. I I I am I'm just presenting what these guarantees are. I think it's, instead of just rejecting them outright, it is important for us as academics to, or as students, to kind of at least push these technologies up to the point, and perhaps we may be able to find better probabilistic guarantees where, things will be acceptable. Okay, so I have to. Okay, I'm going to. I think I am obviously going very slow. I uh, let me explain this. Let me come back to my atomic swap example, and I think we'll have to do some major surgery in terms of my talk. Okay, so here is the outline of the protocol. So what you have is Alice and Bob have agreed to do the exchange. So what Alice does, it creates a secret and uses that secret, hides that secret in a hash function, and makes that value public, and basically puts a transaction, a conditional transaction, if I may, on the Bitcoin blockchain, saying that if Bob can provide me with the secret, then I'm I'm willing to give X Bitcoins to Bob. So that's the conditional transaction that has been added to the blockchain. Okay, so that's what Alice does. So effectively, what Alice has done is she has locked kind of X Bitcoins in this transaction, which is referred to as a smart contract in the Bitcoin and blockchain lingo. Now, what Bob does is he does something analogous. He basically says that move the Y Ethereum that I have agreed to and provide it to Alice if Alice can provide me the secret S. So he uses the same value H. Okay, so he doesn't know the S, but this H has become public as part of the publishing of the T1. As part of the publishing of T1, what has become public is this value H. And he uses this H, Bob uses this H and locks essentially this transaction. Okay. Now, once this transaction becomes public, what happens is Alice can provide the secret because she knows that, and unlock that value, those Y ethers in this blockchain. So effectively, this transaction gets completed and Alice gets her money. But in doing so, what she has done is that she has revealed the secret S that Bob needs to unlock the money that has been logged in the transaction T1. And that's what happens. So Bob takes that secret and gets the transfer of those Bitcoins to it. Okay. So this is all good, but things can go. I see some questions. Let me just see.
So Divi, the question was by Professor Srinath from IIIT Bangalore, saying, why can't we use the classical three-phase commit protocol for doing these cross-chain atomic swaps?
Yes. So Srinath, can you? So Jayant, these are very good questions.
Okay.
I don't know. I'm really slow. I'm going to come to that. How we can leverage database technology to do this atomic swap. There are some wrinkles that have to be worked out, but you are right exactly to the point is that, why don't we use those techniques to do the, so that's
Yeah, and
perfectly
Divi,
reasonable question.
Divi, since there's so much interest here, we can probably go on another 5 or
Yeah, so
10 minutes because
yes,
there is a break after this session. So we can probably steal a little bit of that so that we can host all the
yeah,
questions.
okay. I need to, so this is, I'm trying to get rid of my laser so that I can, okay. Okay, so the problem is that if both Alice and Bob are good people, trusted entities, and they do they act on their commitment responsibly, then everything is good. But what can happen is that these are obviously, you cannot trust each, you don't, they can potentially, Bob could be malicious. And what can happen is Alice and Bob may agree, okay, this is what we are going to do. And Alice puts up her transaction, meaning effectively locks her bitcoins into the Bitcoin blockchain. And at that point, Bob says, oh, I'm not interested, I'm going to go away. Okay. So what has happened in here is essentially, not, if there is nothing can be done because Alice's bitcoins are locked for good. Okay, so what you have gotten here is a conforming party, which is Alice, ends up worse off because Bob did not follow his side of the bargain. Okay, so what Nolan came up with is this idea of time locks. And so he basically has the following kind of variation, where what you do is you basically lock the bitcoins for a certain duration. And the duration that he stipulated, that if Bob does not provide this particular secret within 48 hours, then effectively that those bitcoins are going to go back to Alice. Okay, so that's the classical timeout type of an idea. and and what Nolan does is the same. And in the case of Nolan, he chooses the timeout, which is 24 hours. And the reason the reason of 24 hours and 48 hours is relatively arbitrary. There is some connection, but one thing you have to notice is Nolan's timeout has to be less than what Alice uses, because the secret has to be revealed first from Alice. Okay, until Alice reveals her secret, Bob cannot do anything. Okay, so that's the idea. And the question is how to determine the timeout period of a time lock. And that work, I'm going to skip on some slides. I just want to mention is that the 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 original protocol that I've just described or laid out is by Nolan. And and Maurice Hurley uh, published a, a paper in 2018 which formalizes this notion of atomic swap, and actually shows us how to do these, how to achieve this, uh, how to figure out the timestamps and things like that. So okay, but unfortunately, what happens is this protocol is not completely safe, and the following problem can happen. The problem that can happen is, after Alice has revealed the secret, okay, Bob has to wait for that secret to become public, and he has some time during which he can he can use that secret to unlock the Bitcoin that have been locked in the Bitcoin blockchain. What can happen is, during that time that that Bob has to take that action, he could be failed because of the denial of service. And what can happen effectively is that the timeout will expire, and Alice would have gotten the ethers as well as the bitcoins. So essentially, what does is, there is an atomicity violation in the context of this protocol. Okay, so there are some questions. Arjun, I think we'll have to take some of these questions offline. I I am and I think I see some. Okay, so so that's so this is the problem, and the question is, can we do something about it? And I am going to So in VLDB 2020, we published a paper which is basically presents a solution for atomic swap problem, which solves this atomicity violation. And concurrently in that conference, there is a paper by Hurley, Shira, and Liskov, which is not referred to as cross-chain swaps, but it is referred to as cross-chain deals. But they also use a very similar kind of, at a philosophical level, they use the same principle. And the principle is based on this notion of atomic commitment. And I'm going to rush through this because I think everyone knows that. So the idea is basically, the question is, why don't we use, we as database folks have been doing transaction commitment in a distributed setting for a long time, and the two-phase commit protocol, goes back to uh, a very well-known protocol by Jim Gray and et al. And the idea is essentially what happens is you you have a coordinator, a centralized coordinator, or one of the entities act as a coordinator, kind of asks for the votes from the participating entities, and if they all vote yes, then you basically are committed. If any of them disagrees to not participate in the transaction, then the transaction is aborted. So there is this all or none property, which is what we want in the context. Okay, so what I'm going to do is I'm going to give you a very high level idea. So the idea would be is that we want to mimic this functionality. So just remember, we want to mimic this kind of atomic commitment uh, property in the context of blockchain. So think of it that we have two blockchains, right? Now the problem in the setting that we have in that distributed transactions cases, there is a notion of a centralized coordinator, right? Given that we are in a decentralized environment, we cannot use one of the nodes as a coordinator, right? Because what can happen is you use that node as a coordinator, and what happens if that node is a malicious entity? So remember, I think the underlying theme in the Bitcoin context is you cannot trust anyone. So there is underlying complete mistrust, and you have no idea who could be a malicious entity. And the goal is the system as a whole has to come up with mechanisms that is going to disincentivize this type of malicious activity. Okay, so the idea would be is, instead of using a centralized coordinator, we can use another blockchain. For simplicity, I'm just saying, so you have blockchain, Bitcoin and Ethereum. I can use another blockchain as a representative of a coordinator for atomic swaps between these two currencies, right? So that's the idea. So the so we call that the witness blockchain, which is going to be the witness for the atomic swap. And the witness blockchain is going to kind of do the verification of that both Bob and Alice have kind of inputted their transactions on their respective blockchains. And once that can be verified, then the witness blockchain is going to put a decision that, okay, that atomic swap is complete. And then this decision can be verified by the respective entities, the asset blockchains, Ethereum and Bitcoin, and they can see that the result in the witness is available, and based on that, they can execute that transaction. So that's the idea. So that's basically how we achieve that. Now the difference here is that, unlike in two-phase commit, the votes and the decisions are sent through message passing, and here you cannot rely on message passing, right? So the way that has to happen is, and so essentially what has to happen in the context of the blockchain is this verification of the votes and the verification of the decision has to be done as an evidence of something has been put on the blockchain, right? So that's given the lack of time, I'm not going to go over the details, but basically what's going to happen is that if you are the 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 blockchain who wants to verify that Bob has put his transaction on his blockchain, then you have this particular blockchain has to provide the evidence that indeed this transaction has been put. And this evidence has to be put in terms of the headers of these transactions. So that's in some sense what you have to do is effectively a blockchain has to be able to verify transactions in another blockchain. So in order to avoid that, we basically do this verification using the header information that is embedded in the blockchain. So I'm going to leave that. So this evidence is used, and based on this evidence, we can do the classical two-phase commit. So I'm going to summarize
So Divi,
this.
can we finish in the next few minutes so that there's some time for questions if
Yeah, yes. So
it's okay
I'm
with you
going to.
guys?
I think I wanted to say a few things about permission, but I'm going to leave it at that and I make the connection, and I'm going to conclude. So so the idea is very similar to two-phase commit, except that instead of a coordinator, you have a decentralized blockchain, and and the communication of the vote and the decision is happening by basically verifying if certain transactions appear on different blockchains. So that's the idea. I'm going to refer to the details in the VLDB 2020 paper. Okay, so that's what blockchain. So the question is, what does all this that I have described has to do with big data? So my transition would have been is that what blockchain provides is a storage substrate which has a lot of desirable properties that are relevant in the context of many data rich applications. So in particular, I think if you have, you know, uh, entities that are or enterprises that are kind of collaborating in a combined effort. So typically, the supply chain type of a situation where many entities are involved, instead of relying on a single kind of trusted infrastructure, you could allow using this blockchain type of technology where really you can have, even though you don't have trust, you can still have meaningful progress in such a system. And that class of blockchain or a substrate is referred to as permission blockchain. And I think in my mind, that is very relevant in the context of database systems. And I'm going to just use one slide to summarize that. But what happens is, so in unlike in the context of the pure cryptocurrency and Bitcoin application, what happens is once you are in a permission blockchain, what happens is that you have a set of known identified participants. So what that immediately does is we can now use the classical consensus mechanism that we are very familiar with. They can be used in this context. And once you bring that there, then the issue of latency and throughput, even though these protocols are expensive, they are not as expensive as they were in the context of Bitcoin. So that's the idea. And in the context of permission blockchain, there are many interesting issues that arise. And I think so there is an issue of performance. What happens is some of the in the early generation of permission blockchains, what they were doing is they were basically mimicking the Bitcoin approach where a transaction at a time was being executed. Effectively, what they were doing is they were executing transactions in a serial manner. So the question is, that's an overkill in a large system. You want to be able to execute transactions in parallel, and there are some results. People have looked at it. doing things in an optimistic manner. So using some traditional database approaches in the context of permission blockchains, and that gives rise to much better performance. There is the issue of scalability, which is again, in a large network, you can use database sharding techniques and be able to scale the transactions. And I'm going, the given you are in a sort of a collective environment, you also want to maintain confidentiality of transactions that are completely kind of private to your enterprise. And the question is, how do you achieve that? And finally, you want to be able to do some verification of the transactions are doing what they are supposed to do or not. So there are some results in this area, interesting results, and I think I'm going to leave it at that. I apologize for run doing going so slow. So I was planning to go into the performance and scalability, but I'm going to conclude with some. So from a from a classical blockchain perspective, the question is, you know, they are being proposed as a solution for an kind of an era where we have the question of trust has become an important issue in many of these large systems. So for example, I just want to mention is in the context of advertising networks, right? There is the the current paradigm of having dominant advertising sort of facilitators, and I'm not going to name, but there are, just a few of them. And the question is, can we replace them by having something similar to a blockchain technology? Okay, so there is a lot of activity. If you go and look into, the advertising kind of forums, they are starting to talk about replacing the centralized trusted in supposedly trusted infrastructure who are dominant players in the market, and replacing them by the blockchain. But before we do that, we have to ask ourselves the cost at which we are able to achieve what Bitcoin and other cryptocurrency networks are doing. So the proof of work consumes resources at a planetary scale. I mean, it's the essentially what you're doing is the puzzle solving is an exhaustive computation, and it is really wasteful in some sense. There is a notion that supposedly the blockchain and cryptocurrency democratizes kind of the notion of who controls it, but that's not true, because it is known that there is a handful of miner which control the progress of a Bitcoin blockchain. There is also this notion of security, that everything is once you have private key and public key, then you are secure, but the individual is vulnerable to security of his or her key. There have been instances where people have lost, you know their keys, and as a result have had significant losses. On the right hand side, what I have is that, we are talking about, extreme the decentralization at an extreme scale. And the question is it really worth it? Similarly, replication and redundancy, is this level of redundancy is what we need? And 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 there is, of course, something which is outside my area of expertise. Some people question that the pure Bitcoin blockchains are also, you know could also be used for dark causes, and that has social consequences, and we have to be worried about it. So 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 I'm going to leave that, but all I would like to say is I would like to make the following observation. If you go back in the early 2000s, there was a, peer-to-peer computing came around, and there was a lot of excitement and things like that. But what happened from there is that P2P, for various reasons, really did not kind of stayed with us. But many of the things that were kind of developed in the context of P2P was used in the context of cloud computing. So when a few years down the road, when data centers and the cloud technology came around, many of the P2P approaches that we were using to manage large networks were used in the cloud computing context. So my take is in the same vein. I think there are a lot of, we need to study the blockchain and the impact on cryptocurrencies and things like that. But I think the the what's going to happen is I think many of the techniques that are going to be coming out of blockchain, we can take that to build this notion of permission blockchains that is being used widely. And I think that's where the big uh, contribution we as a database community can make. So that's, I think, is what my closing thoughts are. So
Okay, so
Jayant,
the
I'm going
audience,
to hand it
please,
over to you.
sure, thanks. So please join me in thanking Divi for an extremely informative and stimulating talk on a red hot technology with a virtual clap. Yeah. Since we have run over time, I'll just have this very last question, which is by Swaminathan Shankarnarayan. And he asked the question of whether there's a possibility of using blockchains for e-governance. The question is posed in the Indian context, but you might be more familiar with how it's used in the US. So could you just give us your thoughts on using blockchain for societal benefits?
Yeah, so I think the notion of some managing assets, digital assets, sorry, no, managing physical assets using permission blockchain is a very, very viable idea. I think that's so I think I know in the context of I was looking at one of the supply chains. So there is a the Dolby research is a uh, is a company which produces IP for chips, various kinds of chips, right? What they do is they license the technology to chip fabricators all over the world, right? The fabricators in turn kind of fabricate the chips, and those chips get passed on to system integrators which make different types of equipment and so on. Then these equipments go to the to the next step, to the retailers and resellers and things like that. Now what Dolby is interested is they want to make sure that when they license the technology, that somehow the licensed technology is tracked throughout the supply chain, and they are not cheated by by malicious fabricators, because you have fabricators all over the world, and they can't physically keep track of what they are doing. But essentially having something like a common infrastructure which kind of works across the supply chain is a very, very intriguing idea, and is something that is eventually going to happen. I think this type of technique is already being used in by some of the big retailers, for example Walmart, to keep track of their supply chain, incoming supply chain of food supplies, for example. So I think it is a very promising technology, and I think it is going to it is going to take hold.
Okay, so we will end the session here, and thank you very much again, Divi. So the next session will start in about 15 minutes time. So we hope to see you all back here for those multiple parallel sessions, which will be going on from 10:30 onwards.
Jayant,
Thanks for being a very participative audience. Sharat, you wanted to add something? Yeah.
so Jayant, maybe because there may be many more questions for Divi.
Yeah.
Divi, this is a great talk, so we loved it. But is there a way that we can follow up with Divi and sort of ask if audience wants to ask more questions?
I mean,
Can you give your private number?
so I think, Jayant, I don't know if, I mean, people who want to leave, they can leave, and if there are some interested people who want to be around, I can spend next few minutes talking to them. and we can have
Sure. And I
interactive
also
session.
think
If
on
that,
the VC site, there is a separate chat channel also where people can put the questions up asynchronously so that you can also respond to them at your leisure. Uh, Indrajit, correct me if I'm wrong on that, but that's also possible, right?
yeah, so what has happened is I was not able to log into that registration site. I completed my registration, but somehow I was not able to log in.
Okay, we will make sure that the credentials reach you, but some of the audience can also put up the questions asynchronously, and Professor Agrawal will respond to you at a later time. And Indrajit or Shaurya, anything you'd like to add to this?
No, both options work good, Jayant. Professor Agarwal can actually, we can help him to log into the website and see if and he can respond there. But as Professor Agarwal offered, I mean, if some of the audience member wants to stay back, they can interact
Yeah.
with him.
So I don't know if Arjun is still around. I think he was asking some uh, deeper questions. Arjun, you can send me an email with your questions, and we can interact separately.
So Divi, I
Okay.
had a question for you if you're moving to the session.
Yeah.
Okay, so tell me one. So in the context of the Bitcoin stuff, right?
Mhm.
Money when it exchanges, it appears to me each Bitcoin has stored the provenance of the where it came from, right?
Mhm.
So doesn't the size of the representation keep increasing?
Yeah. So I think it's a combination of so it's a combination of kind of a SHA-256 type of technique to compress the you know the information, and a Merkle tree. I think is that these are the two things that are used to keep track of things. So you really don't carry the baggage around. You really have pointers to the appropriate places. That's how it works.
I see. So it's independent of the number of hands it has exchanged.
Yeah, it is independent of the number of hands. So in that sense, it kind of remains fixed. The validity can be, the assumption is that the hashes don't collide, right? That's the assumption. Uh, and the other thing is, I also want to say is that actually it's not it's actually more complex than that. You can actually have the merges and the splits. So so unlike in our case, a dollar bill, you cannot tear it into half and give it to two people and saying, here is 50 cents for you and here is 50 cents for you. What you can do in Bitcoin context or a cryptocurrency context is you can split your content into many parts. And so you can do the splits, you can do the merges also. So you could have money flowing from multiple directions, and you can consolidate all that and you can merge. So all these things can happen, and that it's all can be maintained. So I think the storage mechanism is relying on the the Merkle tree, and that's how it works.
I see.
Is Arjun here? Arjun Ramesh?
Yeah, I'm not sure whether they can actually directly speak to you
Oh, I
because they
see.
haven't muted, but they
I
could be
see.
on Q&A.
Let me see. Let
Uh,
me see. So he has a couple of questions. So this, in case of atomic swap transaction failure, and when the bitcoins are reverted, will this not cause issues for the ledgers added during the period, or is a separate fork maintained for every cross transaction? I don't understand the question completely. So that's.
Maybe the simple answer would be to read the paper. You have written so many of them.
No. I think I understand what he's saying. Is
Okay.
I think what he's saying is. The So, Arjun, the answer to, if you are still around, the answer to that is that, although I was presenting them as transactions, they're not really transactions. There is this notion of smart contracts. So you can think of them as live object states, which kind of gets transformed as things happen to it. So that's, I think, is the answer to your question. So what he's asking is, the transaction, you put money in the transaction and then you give it back. So is that wrong? So that's how it's positioned as a smart contract, and the state gets transformed as progress happens.
So,
Agrawal,
Divi, since yeah, Shaurya, you wanted to add something?
no, yeah, Jayant, I just sorry to interrupt, but we have the next session starting in 10 minutes. So
Okay. So I'm going to sign off, guys. Thank you very much.
We know it's
Thank you.
late in California, but thanks very much again, Divi, for the wonderful talk.
Yeah, Jen. Thank you.